Start this up. Okay. So you should have gotten an email from Gradescope. So test number 3 is marked. Check your My Okanagan email. Okanagan email. Oops, can't write it all today. For an email from Gradescope. And that's how you'll be able to see your test 3. And then, of course, if you have any questions, then just let me know. But otherwise, there they are. It's kind of generic feedback, but at least it'll kind of point you in the right direction. So Steve and I did split the marking. So if you have any questions about how it was marked or whatever, then just let me know and we can have a look at it. I'll send out an email about uploading a practice assignment to Gradescope. And so I will send an email about uploading a practice document to Gradescope. Because we will use Gradescope for test 4, for test number 4, and the final. Okay. So we want to do a little fake test, so you can have time to figure it out, and then we'll be prepared for when we do test 4 and the final. Okay, so today we're doing sections, so 2 sections, 4.2 and 4.3. Okay. And so, well, that's what I'm hoping. And then if we don't have time to finish 4.3, that's fine. We'll have time next day, but it'll just be nice to get them out of the way. And then so for the remaining time, we only have sections 4.4 and 4.7. So once we're through 4.3, we're kind of on easy street here. So if we can do that today, then that'll be good. Let's see here. Oh, we talked about last day. If you do have a question, then send a chat to everyone, because that'll pop up on my my second screen that I have up here, because I can't see anything here. So on my laptop or on my iPad. All right. Let's do 4.2 then. Section 4.2 is the mean value theorem. Oops. The mean value theorem. Oh. Sorry, I've been writing all morning, but you wouldn't think so. The mean value theorem, which we can abbreviate MVT. Mean is the average, right? So in case you haven't taken any stats, then that's usually where you're introduced to the mean is just another word for the average. But so the mean value theorem we're going to use later on. But before we introduce that, we're going to talk about Rolle's theorem. Rolle's theorem. So Rolle's theorem says that if we let f be a function course, that satisfies the criteria. And there's 3 things it has to satisfy. The first 2 are pretty obvious. F is continuous on a closed interval AB. Maybe the closed interval part isn't obvious, but F is usually, we have to assume that it's continuous, or we have to show that it's continuous. The second criteria is that F is differentiable, right? So we can find the derivative of this thing, differentiable on the open interval AB. So what that's saying is that we're allowing for non-differentiable endpoints, right? And so here, right, we're allowing for non-differentiable endpoints when we're using that, the open interval. But otherwise, what this is saying is that there are no places in the interval where f prime of c, so some point, does not exist, right? Which means we have no corners, so we can't have any spikes like that, right? And no vertical tangents. And that's another way that these things could not exist. We'll say here, f prime at c does not exist. And here, f prime of c does not exist. Right, and so we can't have anything like that. So it has to be differentiable on the endpoint, or on the interval, sorry, and not necessarily on the endpoints. The third criteria is the weird criteria. F of A has to equal f of B. Remember, A and B are the endpoints of this thing, right? A and B. And so what this is saying is that we have to end up at the same y value at the beginning and at the end. So here, this is saying that the endpoints have the same y value. So then the theorem, so we're talking about Rolle's theorem. So if these criteria are all satisfied, then there exists a value c, then there exists a value c in the open interval AB such that f prime of c equals 0. What does this mean? This means the slope of the tangent is 0, right? So it basically means that we've got some sort of cusp, right? And so there's actually a couple of different ways that it could happen. So what I'm going to do is we're going to draw out just 3 different scenarios. There's other scenarios, but there's 2 where Rolle's theorem applies, and then 1 in the middle that we'll look at where it doesn't apply. So if we look at these criteria, right, the last criteria is that the endpoints have the same y value. And so if we do something like, okay, well, if this is at A and this is at B, right, then we're at the same y value. Right? So that criteria is satisfied. Then if our curve looks something like this, whee, right? Then we've got some sort of tangent line here at C, right, where the slope of the tangent is 0. Okay? And so here, we would say C satisfies Rolle's theorem. Satisfies Rolle's theorem. Oops. And so Rolle's theorem is, if you think about it, pretty obvious, right? If you start at one point and then you go to the same y value, at some point, whether you're kind of going down or you're going up, at some point, right, there has to be a change where we're at a peak or at a valley, right? So a maximum or a minimum in between these points so that we can return to the same end point. Right? One option where Rolle's theorem does not apply, right? We can start at this point, and if we fix this endpoint here, so A, B, right? So far so good. We're at the same y value. But if our graph looks something like right, then at these points, right, it's not differentiable because we said we can't have any corners. And so here what we're saying is y equals f of x is not differentiable, over AB. Therefore, Rolle's theorem does not apply. Same thing here. I'm going to start a little bit higher, but I'll end at the same y value. You'll see why in a bit here. So I want to go all over the place on this one, right? We could even have something like this. Whee! Right? We could have more than one tangent line of 0. Right? So this one and this one. Both of these x values satisfy Rolle's theorem. Both x values satisfy Rolle's theorem. So I guess I should put a box around Rolle's theorem because it's pretty important here. A little bit big. Rolle's theorem. Boop-a-doo. Here. I'll end it there in the definition. Yep. Okay. And then those are just some examples. So how do we use Rolle's theorem, or why do we use it? We're going to use it to be able to argue how many solutions we might have, right? And so if we know that we reach a peak once, right, then we know that we're going to have 2 solutions, right? And so if you reach a peak twice, like here, right, then you would have 1, 2, 3 points where you would have these solutions, right? And so that's where we're headed. So we'll start talking about Rolle's theorem and polynomials. What's nice about polynomials, right, is that they are always continuous, and they're always differentiable, right? And so if we're talking about, if we specify and talk about quadratics, right, then we have f of x is ax squared plus bx plus c, right, where a, b, and c are constants. Put a little note here. Polynomials are continuous and differentiable on the set of real numbers, right? And so that's good, because then we've satisfied the first two conditions, or the first two criteria. So what we want to know is how many solutions to f of x equals ax squared plus bx plus c equals 0 are there? We know from experience, right, that we've got this quadratic, and so we know that there could either be 0, 1, or 2 solutions. And so do a little. We could have 0, 1, or 2 solutions. Why can't we have 3? Right? Let's talk about why it can't be 3, because that's going to be kind of useful to have that skill later on. So it is impossible for ax squared plus bx plus c equals 0 to equal 0 at 3 values, because, well, what would that look like? We would have some sort of graph that looks like this, and we cross the x-axis here, here, and here, right? That would be 3 values. And so now, I'm kind of coming along here. Maybe I look like this. Whee! Right? Maybe it looks something like that. So what we'll argue is that if there are 3 solutions, right, to f of x equals 0, just using that shorthand for the quadratic, then there are 2 horizontal tangent lines. Horizontal tangent lines. Right, and just to kind of use a different color here, horizontal tangent lines, those would be here and here, and the 3 solutions would be the pink dots, right? And so then we would have 2 horizontal tangent lines where it goes and kind of curves and is a maximum or a minimum. So then this means that f prime of x equals 0 at 2 places, right? So what we can do is we can still, even though we've got this generic quadratic equation, right, we can still find the derivative. And so what we can do is we can say, well, f prime of x is actually going to be, we've got ax squared, so we've got 2ax plus b, right? That's the derivative. So now if I take the derivative 2ax plus b, force it to equal 0, then fine. If I'm able to find 2 x values that make this happen, then all right, we're defeated, right? But what we'll find is that there's only one value. And so we've got 2ax is negative b. So x must be negative b over 2a. Here, what we're finding, right, this is only one value. This tells us that there's only one horizontal tangent line. So that's why, right, we can't have 3 solutions. We can have at most 2 solutions, right? And so how many solutions to f of x equals ax squared plus bx plus c equals 0 are there, right? We're deciding, okay, we could have 0, 1, or 2, right? And then here, all we did was argue that we can't have 3 solutions because there's actually only one horizontal tangent line. So what we're going to do, we can apply the same theorem, Rolle's theorem, to other functions in the same way. So we can apply, or maybe I should put a little summary here. Just bump it down a line. Therefore, f of x equals ax squared plus bx plus c equals 0 can have at most 2 solutions. There. So we can apply, so that's our answer to that previous question that we were working on. So we can apply Rolle's theorem to other functions the same way. To other functions the same way. So as just an example, right, if we've got, and just for space issues, I'm going to bump that up here. If we've got f of x equals something like x to the 3 plus x minus 1, right? Remember from, I think it was on test 2, I want to say, but also in chapter 2, we use the intermediate value theorem. And so here, in chapter 2, right, we showed that f of x has at least one solution, using the intermediate value theorem. Okay. So now, so that's a good start, right? So we're able to show, okay, if we're able to prove that this thing has at least one solution, then we can use Rolle's theorem, right, chapter 4, to show that f of x equals 0 having 2 solutions, for example, is impossible using Rolle's theorem. So it's kind of a proof by contradiction situation. Is impossible using Rolle's theorem. So together, right, what can we conclude? Right, if we're able to show that, okay, we have at least one solution, but also having 2 solutions, 2 or more solutions, I guess it should say, having 2 or more solutions is impossible, well, then what do we land at? There must be only one solution to f of x equals 0. Yeah. going to be broken up over the page, but I guess that's okay. So let's do an example of this where we actually use it. So, and we'll use that function that we were just talking about. Show that x to the 3 plus x minus 1 equals 0 has exactly one solution. Has exactly one solution. So here, right, we said, okay, first thing I'm going to do is I'm going to use the intermediate value theorem to show that there's at least one solution. And then I'll step in with Rolle's theorem to show that there can't be more than one solution. So step one, oops, I'll just use one. Step one is the intermediate value theorem. First thing we have to check is f of x continuous? Right, otherwise we can't keep going. Yes, it is, because it's a polynomial, right? So it's continuous over all real numbers. So remember what we did for the intermediate value theorem? Usually if I give you some endpoints, right, so on some interval, then you plug in the endpoints and you're hoping to see a negative result and then a positive result, or at least on opposite sides of 0, right? Here we don't have an interval, so we're going to have to pick some values. But usually if we kind of don't go too crazy, choose values of A and B to test, right? If we let A be 0, for example, see what happens. Then we get f of A is f of 0, and we've got 0 to the power of 3 plus 0 minus 1, putting me at -1, which is less than 0. And how about if we use b of 1, right? So the interval 0, 1 is what I'm zooming in on here. And so I've got f of b is f of 1, 1 to the 3 plus 1 minus 1, puts me at 1 plus 1 minus 1, positive 1, which is greater than 0, right? So somewhere between 0 and 1, right, this thing went from negative to positive, and so at some point in between here, it must have crossed 0, right? So 0 is between f of A and f of B, f of A and f of B. Therefore, by the intermediate value theorem, IVT, there is a value C. There is a value C in the interval 0, 1, where f of C equals 0. Right? So there is at least one solution, right? There could be more, but we know because we've narrowed it down, and we narrowed it down pretty quickly to 0, 1, somewhere between there, it crosses the x-axis. Okay. If we move on to step 2, so now we've shown that there's at least one solution. Now we want to show, using Rolle's theorem, that there can only be one solution, right? No more. So we want to show that f of x equals 0 cannot have two solutions, or cannot have more than one solution. So what we do is that we can argue, right? Well, what if we say that there are two solutions, and then if we're able to prove that that's not the case, then that's good. So if f of x equals 0 has two solutions, right? Let's say x equals c1 and x equals c2, then f prime of x equals 0, right? So now we're talking about the derivative. So, right, if we go back to that graph of Rolle's theorem, right, if we have two solutions, right, at x equals c1 and c2, right, then here f prime of x equals 0, right, at some point between c1 and c2. And so what we've got, then f prime of x equals 0 at some point between c1 and c2 since f is differentiable over the set of real numbers. I think we established that. I'm pretty sure that we established that it's continuous and differentiable. Oh, no, we didn't. Right? But here, right, what we can start by saying is polynomials are continuous and differentiable over the set of real numbers. Okay. So, so we're able to use those facts. All right. So what we're saying is that, okay, if we have more than one solution, right, C1 and C2, then at some point, then we're going to have a slope of 0. So what we're going to do is we're going to find f prime of x. Right. Well, if f prime of x, so f of x, if just so I don't have to scroll around, is x to the 3 plus x minus 1. So f prime of x must be 3x squared plus 1. I'll finish here. Find f prime of x equal to 0. If I have 3x squared plus 1 equals 0, right, what values of x make this 0? Well, I get 3x squared is -1, so x squared is -1 over 3. I can't take the square root of a negative number, right? And so this thing has no solutions. Okay. Which tells me that f of x has no horizontal slope. Has no horizontal slope. This means that f of x equals 0 cannot have a second solution. Right? Because we said, okay, let's assume that there are two solutions. Then they would look something like this, but then we know that we're going to find a horizontal tangent line between them, right? And so what we're finding here is we actually find no solutions to where the derivative is 0. And so that means So therefore, f of x equals x to the 3 plus x minus 1 equals 0 has exactly one solution, right? Because we were able to prove that, solution, not solutions. We were able to prove that there couldn't be more than one. We showed that there was at least one in step 1, but then in step 2, we're able to show that we can't have more than one. Right? So then we can land on that we have exactly one. I'll check for questions here, but I see none. Okay. So that's Rolle's theorem. Kind of similar. Let's talk about the mean value theorem, which was the title of the section. So kind of a big deal here. So the mean value theorem MVT says that if we let f be a function, and same criteria, right? That f has to be continuous on some interval and differentiable on the open interval. So pretty standard criteria. So it's a good idea if you just start a question by checking to see if it's continuous and differentiable. Remember at the beginning of the term, we talked about all the continuous functions, right? So things like sine, cosine, polynomials, right? We had a couple of different functions that would be continuous. And so let f be a function that satisfies two criteria. First one being f is continuous. Oops. F is continuous on the closed interval AB. So it's always continuous. And the second is f is differentiable on the open interval AB. So again, leaving room for non-differentiable endpoints, right? But we already discussed that, so I'll finish the theorem here. Then at some value c, in the open interval AB, we will have something that looks like this. F prime of c is going to be the same as f of b minus f of a over b minus a. Okay. Notice that these are the same. So a and b, or sorry, b and a, I guess. So what this is saying, right, is that this is the slope of the tangent line at C, right, is going to be the same as, so between A and B, well, A and B are the endpoints, right? And so this is the slope, right? Rise over run. This is the slope of the secant line connecting the endpoints. Slope of the secant line connecting the endpoints A and B. Just gonna squeeze that in on the same page. Okay. So, pretty cool. Let's put a box around this. It's the name of the section after all. Must be kind of important. All right. Let's see what this looks like in an example. So if we have f of x equals 2x squared minus, minus 3x plus 1 on the closed interval 0, 2. What this thing might look like, or would look like, except I'm not very good at drawing, so here we go. I would start somewhere here at 0, 1, right? If I plug in 0 into here, then I get 0, 1. And if I plug in 2 into my function, I see that I end up at 4 minus 6 plus, 8 minus 6 plus 1. So 2, 3. Let's put it somewhere, I don't know, here. 2, 3, not to scale. So, and it might look something like this. Here's our curve. Actually, I'll make it more bold. Maybe. There. How about that? Shouldn't drop down so much here, but that's okay, whatever. Okay, so what the mean value theorem is saying is that, okay, we've got this point, A is at 0, and then here we were at 2. Okay. What we're going to find is that, well, we can find the slope of the secant line, right? The slope of the secant line is the line that connects these two here. Right? And so the slope of the secant line is f of 2 minus f of 0 over 2 minus 0, which is 3 minus 1 over 2 minus 0, putting me at 2 over 2, which is just 1. Right? So here, I know that I have a slope of 1. Okay. What this is telling me, right, is that at some point, so the mean value theorem says that at some point between, so on this interval, there is a point that has the same slope of the tangent line as the slope of the secant line from the two endpoints, right? So what we're going to do is say that by the mean value theorem, f prime of x equals 1 at some point, right? And maybe I'll just use the same color here, is 1, right? Because this is what it is and where it came from. Since f of x is continuous and differentiable. Hopefully you guys don't mind me shortening those, continuous and differentiable. So what we can do, right, we can find the derivative of this thing. It's just a polynomial, so no big deal, right? And so we can find f prime of x is 4x minus 3. Where is this thing equal to 1? Well, 4x minus 3 equals 1 if 4x equals 3, so if x is 3 over 4. Ha. Fail. Sleep on the job here. 1 plus 3 is 4, so x must be 1. Okay. So therefore, at x equals 1, the slope of the tangent is the same as the slope of the secant line connecting the endpoints. So somewhere up here, right, what we found was that, let's make this one here, not quite parallel looking, were they? The slope of that thing is 1 as well, and I guess, didn't really do a good job here. There. Maybe I have to cheat and move my 1 over. There. Now they're parallel and sort of at 1, but off center. Okay. So how can we use this? Let's look at a kind of a fun example. So example, looking at Google Maps. The distance from Kelowna to downtown Vancouver is 392 kilometers. If we leave at 1:13 p.m., it predicts we will arrive at 5:33 p.m. Pretty fast, if you ask me, but whatever. You know, and so what we might want to know is, well, we can look at the average speed, and then we can look at just kind of how we're able to drive all the way down. And so if we graph this thing, we can put the distance on the y-axis, can put time on the x-axis, right? It might look a little bit weird, but if I leave at 1:13 p.m. and I'm arriving at 5:33 p.m., I'm more of a 24-hour clock myself, but whatever. Here, when I leave, I've gone a distance of 0, right? But when I arrive, I'll have gone a distance of 392. So our distance traveled would end up here, right? Somewhere in between here, right? Our path to traveling that distance, right, might look something like wee. Right. And what we see is that we've got 2 points here where the slope of the tangent line is the same as the slope of the secant line. Okay, so we can figure out what these velocities are. Okay. So if we're talking about the average speed, right, that's going to be the slope of the secant. That's going to be f of b minus f of a over b minus a, which is, if we kind of use the time as our input, f of 5:33 minus f of 113, I'm going to assume that it's PM, over 533 minus 113. Well, at 533, we'll have traveled a distance of 392, starting from 0. And then one thing to keep in mind, right, is that 533 minus 133, or, sorry, 113, that's 4 hours and 20 minutes, which is 4 hours and 20 over 60. So roughly 4.33 repeating hours. So we can divide by 4.33 repeating, and we get 90.5 kilometers per hour. That's our average speed. What we can say then is by the mean value theorem, your speed f prime of t equals 90.5 kilometers per hour at some time in the interval, from 1:13 p.m. to 5:33 p.m. Check for questions. Okay. I don't find that this is, groundbreaking or anything, but it's just a good thing to be able to use and know, right? And it's kind of cool to know that the slope of the secant line, because that's easy to find, right, is going to translate to the slope of the tangent line at least one point between there, right, regardless of what the function looks like. And so another way that we could use this, let's do another example. Let's see here. The maximum grade for railroad is 2.2%, which is essentially saying that the maximum slope can be 2.2 out of 100. So hopefully you guys know the KVR in Kettle Valley Railroad runs all through the Okanagan. So if the elevation at one point on the KVR, what's happened here? I don't know what that is. Okay, whatever. At one point on the KVR is 360 kilometers. How high is the highest possible point 1,200 kilometers away on the rail line? So how high is the highest possible point 1,200 kilometers away on the rail line? So what we're saying here, right, is that the maximum slope has to be 2.2 over 100. So what we're actually saying is that f prime of x must be less than or equal to 2.2 over 100. And if we let A be 0, which is the current location, and B be 1,200 kilometers away, then we're talking about the interval from 0 to 1,200. Oops, close bracket. So then what we'll say is that by the mean value theorem, I know that f prime of C, just in general, must be f of B minus f of A over B minus A. So the steepest track is if f prime of C is 22 or 2.2 over 100. Let me rewrite that. Because that's the maximum that's allowed, right? So if the maximum slope is 2.2 over 100, then how high is the highest possible point? Well, if we just assume that the slope is at the maximum the whole way, right, then we'll be able to find the highest possible point 1,200 kilometers away. And so if we let the derivative of C, or a derivative at C, be 2.2 over 100 for all C in the interval 0 to 1,200 or 1,200, then we know f of 0 is 360, right? Because that was given. And we want to solve for f of b, right? What's the highest possible point? So now we're solving for f of b. So if we use that same, so f prime of C must be f of b minus f of a over b minus a. Well, if I'm forcing this to be 2.2 over 100, then I've got f of b, which I'm solving for, minus f of a, which we know is 360, over 1,200 minus 0. I can solve this thing for f of b, right? I get 0.022 times 1,200. Oops, let me scoot that over so I can line up my equal signs. There. Is going to be f of b minus 360. If I do 0.022 times 1,200, I get 26.4 plus 360 is f of b. So f of b must be 386.4 meters. So we assume that we're using the highest or the largest possible slope for this thing to be able to find what's the highest possible point 1,200 kilometers away. Therefore, the highest possible point 1,200, is it kilometers? Are these all kilometers or meters? I feel like these should be in meters, probably. Makes a little bit more sense. Let's say that. It doesn't actually change anything. But now I'm in meters. 1,200 meters. I feel like that makes more sense in the question. Knowing something about just elevations and the KVR. So the highest possible point, 1,200 meters away, is 386.4 meters. Okay. Check for questions here, but I see none on that end and none over here. Okay. So let's do section 4.3 then. So section 4.3 kind of moves, well, I mean, this is all looking at a graph too, but section 4.3, I'll put it on a fresh page here. 4.3, we're going to talk about how derivatives affect the shape of a graph. So how derivatives affect the shape of a graph. The shape of a graph. And we've actually already talked about this when we first started talking about the derivative. And so a lot of this, it's not really new. So especially the first derivative, it's not until we get into the second derivative that it might be a little bit newer. But we'll start with the first derivative. The first derivative if the first derivative, so f prime of x is greater than 0 on an interval, we know that f is increasing. And then, oops, if f prime of x is less than 0, right, then we know that f is decreasing. So on an interval, f is decreasing. So from here, there's something called the first derivative test. And so we're going to be able to find if we have a local maximum or minimum, or maybe neither of those. So the first derivative test suppose C, so just some arbitrary C here, suppose C is a critical number, which we introduced last day, but we'll review here, of a continuous function, f, right? And remember, we've got type 1 critical number is if the derivative at C is 0. And we've got a type 2 critical number if f prime of C does not exist, right? So we've got two different ways that we could have critical numbers if the derivative is 0 or if the derivative does not exist. So the first part of the first derivative says that if f prime, so if f prime, the derivative, changes from positive to negative, at x equals c, then f has a local maximum. Right? Because if we go to some point C, right, and at this point we've got the slope is changing from being positive to negative, right? Then we're at a maximum. Right? So pretty, I mean, straightforward stuff here. So if f prime, so if the derivative changes from negative to positive, then of course we've got the other situation, right? Negative to positive, so then we've got a minimum. I'll write out and then draw those. So if the derivative f prime changes from negative to positive at x equals c, then f has a local minimum. So same idea here. If we're at c, then if we're going from a negative slope to a positive slope, then this is a minimum. Right there. The other option, or the third option, is if the derivative doesn't change sign, right? So I'll put this on the new page. If f prime does not change sign, at x equals c, then x equals c does not give a local minimum or a maximum. Then x equals c does not give a local minimum, a local min or max. Yeah. And so what you're going to do to solve these, make a sign chart. Okay. So what you'll have is a couple of critical numbers. So you've got a critical number here, critical number here, critical number here, and then evaluate f prime. It'll either be positive or negative in this region, right? Positive or negative in this region, and positive or negative in this region. And that's how you'll be able to know. So what I'm going to do is I'm going to put a box around the first derivative test, because that's how we're going to find maximums and minimums. Oh, sure, I'll put the sign chart in there too. Oops. There. Okay. So let's do an example of this. Example, if we have f of x is 3x to the 4th minus 4x to the 3 minus 12x squared plus 5, right? The first thing I'm going to check is, well, this is a polynomial, so it's continuous and differentiable. All right, so that's good. Part A, what I want to do is I want to find the critical numbers of f. Find the critical numbers of f. Okay. So first thing, if I have to find the critical numbers, well, that's where the derivative is 0 or it doesn't exist. Because I don't have a fraction here, I really don't think that there's going to be anything. Well, and it's differentiable over all real numbers, but unless I have a fraction in my derivative, then it'll be, or a log or a square root, but I have none of those in my derivative, so the derivative will always exist. So what I'm focusing on is where the derivative is 0. So I get, if I find the derivative, I get 12x to the 3 minus 12x squared minus 24x. So here, I'm going to focus on my type 1 critical numbers, is when this whole thing, 12x to the 3 minus 12x squared minus 24x equals 0. Right. Usually what's going to make things easier is if I'm able to factor this. And so 0, I can factor out a 12x from all of this and end up with x squared minus x minus 2. You could either use the quadratic formula here if you wanted to find the roots, or this one's a little bit easier. So, oops, don't forget the x. So I can just do x minus 2 times x plus 1. Right. But either way, you could figure out what the roots are, even if you don't like factoring, right? Because usually I don't love factoring. So you could just use the quadratic formula to figure out what the roots are. So here, right, this whole thing is going to be 0. If x is 0, right, then everything's being multiplied by 0, so then it goes away. If x is 2, because then we have 2 minus 2, which is 0, so everything goes to 0. Or if x is negative 1, then this whole thing goes to 0 as well. So here we've got x is 0, x is 2, and x is negative 1 are my critical numbers. So type 1 critical numbers are those guys. Negative 1, 0, and 2. Oh. So type 1 critical numbers at x equals negative 1, 0, and 2. Okay. So what I want to do next, right, is I'm going to use the fact that I know that if the derivative is positive, then f is increasing, and then if the derivative is negative, then I know that f is decreasing, right? So for this next part, if we want to find, so state the intervals on which f is increasing and decreasing. On which f is increasing and decreasing. Okay. So what we want to do here is we have to use a sign chart. Well, I mean, you could break it up any old way, but it's going to be easier if we just use our sign chart with our critical numbers here. Let me just center this a little bit here. There. I'm just going to pick some test points here in each of these intervals. And remember that these keep going forever and ever, but there's no more cutoff points, right? Our critical numbers are the only cutoff points. And so just for testing, I'll use values like -5, that's to the left of -1. Between -1 and 0, I've got -0.5, for example. I'm going to use 1 here. And then, I don't know, I'll use 5 here. Just for visualizing. I don't actually need to solve these things. I'm just going to use them to figure out the sign of my derivative. And so what I'm going to use is I'm going to have f prime of x, remember, is 12x times x minus 2 times x minus 1. X minus 2 times x minus 1. Yeah. Now here, what I'm going to do is I'm just going to break this up into whether that's positive or negative, this is positive or negative, and this is positive or negative. So what I get is if I plug in -5, then that first number becomes a negative. -5 minus 2, well, that's also a negative. -5 minus 1 is also a negative, right? So to figure out the sign, I don't actually care about what the values are. I just want to know what the sign is, right? And so here, the derivative is negative, right? A negative times a negative times a negative makes a negative. So here, f prime of x is less than 0, right? So therefore it's decreasing. So we're going to do the same thing in each of these little sections, right? And so in this section, and let's see if I can kind of do a subtle breakup here. So if I do the same thing with -0.5, well, I get a negative times a negative. So -0.5 minus 2 is still negative. -0.5 minus 1, sorry, plus 1. Oops, plus 1. Doesn't change the other one, it was just a mismatch. -0.5 plus 1 is positive, so now I get a negative times a negative times a positive makes a positive. All right, and then do the same thing for the next interval. And notice that you could pick any value inside this interval here, right? I've just picked these kind of arbitrary ones so that it's easier to plug in and kind of check if we get a negative or a positive value here. So same thing using 1, well then I get a positive times 1 minus 2 is a negative times 1 plus 1 is a positive. So here I get a negative value overall. And moving over to the 5 test point, well, I get positives all around now. So it's positive. So what this is going to look like, right, is our f, our function, right here, it's decreasing, and then it's increasing, and then it's decreasing, and then it's increasing. Right. So the question was, state the intervals on which f is increasing and decreasing. And so it's increasing on the intervals from -1 to 0, but not including those 2 points because those make it 0. And then it's increasing again from 2 to infinity, right? So we've got from -1 to 0, and then the intersection, so the union from 2 to infinity. And then it's decreasing on what? Decreasing from -infinity up to -1, and then picking back up at 0 to 2. Right, just double checking here. Nice. Okay, so we found the intervals where it's increasing or decreasing. Now we can use this, right? We can use this behavior because we know we have a critical number at -1, and it's switched from decreasing to increasing. So it looks like I've got a minimum here, and then it switched from increasing to decreasing. So I've got a maximum here, and then same thing here. I've got another minimum over here. So part C, we can classify each critical number as a local max or min. So local max or min, I'll put in brackets, or neither, right? If the sign doesn't change around the critical number, then it's neither. we can say that x equals -1 is a local minimum, right? Because that's what we decided here. X equals 0 is a local maximum, and x equals 2 is a local minimum. Yeah. What we can do, right, is we can even use f of x is what? The original function, 3x to the 4th, and I can just tell I'll need more space here. F of x is 3x to the 4th minus 4x to the 3 minus 12x squared plus 5. And so f of -1, right? What is the value when x is -1? Well, at -1, I've got them here. We're at 0. At f of 0, f of 0 is 5, and f of 2 is -27. So what I can do, if I wanted to, I could sketch this thing out a little bit, except it's going to be hard to accommodate the -27, right? But it might look something like this, where at -1, 0, oh, I guess I should move it out a little bit. -1, 0, and 1 and 2. When it's at -1, it's at 0. When it's at 0, it's at +5. Right, so 0, 5, -1, 0. And then when it's at 2, it's at -27. Let's just put that somewhere down here. 2, -27, because I've got this page break here. So then this thing, I know I was decreasing heading into x equals -1. So I know I'm going to be coming from up here, something like, oops, something like this. And then I know I'm switching. I've got a minimum there, and then I've got a maximum here. And then it kind of keeps going. And then I know it took off this way. Right. Just kind of emphasizing those points. Nice. So that's how we can use, so those are all the ways that we could use the first derivative, right? We can figure out things like, well, where are the critical numbers, right? Where is it increasing and decreasing, right? Where is the first derivative positive or negative? And then finally, we can classify things as a local max or min, or neither, if the sign doesn't change. So let's have a look at the second derivative. We'll check for questions here. See none. The second derivative remember f double prime, well, is the derivative of the first derivative. So is the derivative of the first derivative, right? But what we can say is that f double prime, so the second derivative, is the rate of change of the slope, right? That's another way that we could think about it. And just some things to keep in mind about the second derivative is the second derivative, we can use it to figure out if it's concave up or concave down. And so if f double prime of x is greater than 0, so if it's positive on an interval, oops, on an interval then we say that the f, the function f, is concave up. Oops, concave up on the interval. Right, it doesn't always have to be true. That's why we have to add the on the interval. Right, it's only true for where the second derivative is positive. But so concave up would look something like this, right, where we're kind of facing upwards, right? So we've got this bowl shape. Oops. Bowl shape is concave up, right? If we've got something like this. If the second derivative is less than 0, right? So if it's negative on an interval, let's see, then f is concave down on the interval, which is just the upside down bowl or kind of a hill shape. So if you have something that looks like, whee, then kind of a hill shape is concave down. If we have something that goes like this, so here, if we have something that looks like like this, right, then at some point here, right, it switches from being concave up to concave down. This is what we call the inflection point. Right? That's where it switches. And so if the second derivative, so f double prime changes sign at some point C, so if f double prime changes sign at x equals C, and if f double prime is continuous, of course, continuous at x equals C, then we say f has an inflection point at x equals C. Yeah. So let's do an example. Okay. If we have f of x is x to the power of 3, right, we know that this thing is essentially a polynomial, but we also know that it's continuous and differentiable on the set of real numbers. Can also find this first derivative is 3x squared and the second derivative 6x. First thing I'm going to do is I'm going to use the first derivative to find the critical numbers. So f prime, oops, to find critical numbers, So if I force 3x squared to equal 0, then I've got x squared equals 0. So x must be 0. So then here, if I make a sign chart around 0 and I pick values, convenient values, right, -1 and 1, to see what the derivative looks like here. Let's see here. F prime of x is 3x squared, which is 3 times a positive, right? Here it's obvious, but just to get in the habit of just kind of going for the sign now, right? We're not solving these things because sometimes, well, it's not going to be this simple to solve for, right? But the end goal is to figure out if it's positive or negative, right? And so what we do here on the positive side, now I've got 3 times a positive number, which is also a positive number. Okay. So it looks like we don't have a minimum or a maximum, right? So therefore, no local min or max, right? Because it's just going up and going up. So now, the second derivative, we can check concavity, right, to see what this thing looks like. So we know that the second derivative is 6x, and where 6x equals 0, well, at x equals 0 is where that's going to happen. So it's going to potentially change concavity at 0. Now again, right, if I just pick kind of convenient values around 0 here, my second derivative of x is 6x, which is going to be negative if I give it a negative number, and it's going to be positive if I give it a positive number, right? So what that looks like is I've got this concave down, right, and concave up on the other side of 0. So we can use this information to arrive at f of x equals x to the 3 must look something like this, right? Which we already knew, right? There's no minimum or maximum at 0. No min or max. Here, concave down. And here, concave up. Nice. So, let's talk about the second derivative test. So the second derivative test is, well, kind of riding on the heels of the first derivative test. So the second derivative test suppose the second derivative, f double prime of x, is continuous near C. It's continuous near C. Part A of the second derivative test says that if the first derivative at C is 0, right, which says what? That x equals C is a type 1 critical number, right? And the second derivative at C is greater than 0, right? meaning that it's concave up, then, right, that combination, then f has a local min, then f has a local minimum at x equals c. The second part of that is, again, if the first derivative at c is 0, right, so again, we have a type 1 critical number, and the second derivative at c is less than 0, right, meaning that it's concave down, right, that's the only difference here, concave down, then f has a local, concave down, oh, I wrote minimum on both of these, and now, then f has a local, this is what I have at x equals c, but let me just see if I can, find which one is true. Where did I grab these from? You might have to stop that for a second here and go in here. Top secret. Maximum. That makes sense. Okay. Let me go back here. We're back. Okay. There's a local maximum. Just convincing myself here. If it's concave up, right, then this must be a minimum. If it's concave down, must be a maximum. Good. Even though I stumbled here, we'll put a box around the second derivative test because we have to use it. One note is that notice that we have to have type 1 critical numbers. So it actually can't handle both types of critical numbers, right, where the derivative does not exist. So that's making it not as strong as the first derivative test. So one note is that it's not as strong as the first derivative test. First derivative test. Because it only works with type 1 critical numbers, right? But this works well with polynomials. Works well with polynomials, which honestly we're only going to use here in this course for this type of stuff, as you'll see. Okay. So let's use it in an example. If we have f of x is x to the 4th minus 4x to the 3, I want you to use this, use the second derivative test, use the second derivative test to find all local max and mins. To find all local max and mins. So the first thing we have to do is we have to find the critical numbers. And so the derivative of f is 4x to the 3 minus 12x squared. And we want to force that to be 0. 4x to the 3 minus 12x squared equals 0. Like I said before, one easy way to do this is if you can factor out as much as you can, or factor this thing as much as you can. So then we get 4x squared times x minus 3 must be 0. So here, right, I have a critical number at x equals 0 and a critical number at x equals 3. So my critical numbers are 0 and 3. Find the second derivative. Well, f double prime of x is what? The derivative of the first derivative, which is 12x squared minus 24x. So then what we do is if we've got the second derivative test, right, then we're saying, okay, well, if we've got a type 1 critical number, which we do, right, and the second derivative at that critical number is greater than 0, right, then we have a local minimum, right? So we're going to evaluate the second derivative at the critical number. So then evaluate f double prime of x at the critical numbers. Now we've got more than one, but sometimes there's only one, right? And so at x equals 0, right, I've got f double prime of 0, which is 12 times 0 squared minus 24 times 0. This is equal to 0, right? And so here, that's not an option, right? If we're looking at the second derivative test, it has to be either greater than 0 or less than 0. So if we end up at 0, then we say that the second derivative test fails, right? And so here, the second derivative test fails. So what we're going to do is we're going to use the first derivative test in this case. Right. But we'll keep going. We'll just keep that on the back burner. Let's have a look at x equals 3. We might have to do the same thing at x equals 3. Not likely, but we might. So f double prime at 3 is 12 times 3 squared minus 24 times 3, which is 36. 36 is greater than 0, so it's concave. Oops, concave up. Which means that if it's concave up, right, by the second derivative test, x equals 3 is a local minimum. So if we have to use the first derivative test for that first critical number, right, remember the first derivative is 4x squared times x minus 3. The first derivative test is where we use the sign chart. We're at x equals 0, and I'm just going to pick some test values around 0. -1 and 1 might be nice. Right. And then I know I've got a critical number here at 3, but I also know that that's a minimum. I already decided that. So here, f prime of x is 4x squared times x minus 3, which is 4 times a positive number times -1 minus 3 times a negative number, giving me an overall negative. Here I've got 4 times a positive times 1 minus 3 is a negative. I've got another negative. Right? So here, x equals 0 is neither a min nor a max. Okay. I think what we'll do, I've only got one more example, but it's kind of long. Might be nice to use it for review next day. Any questions though before we kind of pack it in here? Let's see who's all here. Hey guys. All right. No questions? Because what we'll do then is I'll just use that next example for review next day. That'll be good. All right. Gonna stop the recording. I'll wait a little bit for some questions if you have any, but otherwise I'll see you guys. Well, I won't see you. You'll hear from me on Tuesday. All right.